Okay, so this is the homework for the Unit 2 Chain Rule Day. I had a request for some problems from this to be worked out. So when you're using the chain rule, remember, you would use it in an example like this. If you're trying to take the derivative of a function within another function, that is a clue that you want to use chain rule. So here when you use chain rule, you would say that the derivative of x, we're going to take that 6, multiply it by this 1 in front. So it's going to be 6. You recopy what's in the parentheses, and you decrease the exponent by 1, so that becomes the 5th. But then the chain rule says that you have to then take the derivative of what's inside the parentheses there. So the derivative of what's inside there is just a -7. And again, if it was a free response, you'd be more than welcome to leave your answer like this. Or if you wanted, you could rewrite it as -42 times the quantity 8 minus 7x raised to the 5th is your final answer. Okay. For the next one, I would interpret this square root as the whole thing raised to the 1/2 power. So I'm just going to rewrite it as 2x to the 4th plus 1 quantity to the 1/2. Whenever you see square roots, you want to go ahead and rewrite it to the 1/2 power. And now I would apply the chain rule. So again, I note that I'm taking the derivative now with that k prime. So when I take the derivative, it's going to be 1/2. You just recopy the part in parentheses as is. You decrease the exponent by 1, so 1/2 minus 1 is going to be a -1/2, multiplied by the derivative of the inside. So the derivative of that, 4 times 2 is 8x cubed. Okay, and again, you could probably rewrite that if you wanted. Let's see, this is going to be in the denominator, the 2 will be in the denominator, and then this whole thing will be in the denominator because of that negative exponent, and I'm going to take the square root of it. So the only thing left in the numerator, I could use this 2 and take out that to rewrite it as a 4. So I would say the final answer could be something like 4x cubed over, I already got rid of that 2, so then in the denominator it's going to be the square root of 2x to the 4th plus 1. For C, one of the properties of derivatives says that you are allowed to take derivatives term by term. So I'm going to tackle this first term here, and that's going to be using our very simple power rule. So the power rule says if you're trying to take the derivative, and it's fine that it's a theta, you could change it to an x if you prefer. You're just going to go ahead and say that that's going to be 3 theta squared. Okay. Then you're going to have to take the derivative of that second part. Well, remember, this second part, think of that as cosine theta quantity squared. So that's actually going to be a chain rule. Okay. So it's going to be plus 2 cos theta. Okay. Then the derivative of the inside, right? Because the derivative of that cosine of theta, the derivative of cos, is negative sine. And those are multiplied together. So we've got that. And again, that may be rewritten as 3 theta squared minus 2 cos theta sine theta as your final answer there. So the next one is asking you, given some variables here, so notice that this is a polynomial. There's no product rule or anything that needs to happen here. It's just using your straight power rule. So you would say 2 times a to find the derivative. So the derivative there is going to be 2 times a. And then the x will be just to the first power now. Plus, it would just be b. The x will be gone. And then when you take the derivative of a constant, then you aren't left with anything there. So that part's finished. All right, going on to e. Remember, whenever you take the derivative of e to something, well, you just recopy it, and then you take the derivative of the exponent and write it out front. So here, the derivative, so g prime, I recopy it, and that's to the -0.5t. But then I multiply that by the derivative of that exponent. Okay, so the derivative of this exponent is just -0.5t, so -0.5t. And those are all attached by multiplication there, so negative 0.5 times 1,000 leaves you with just a 500. Oh, but it's negative, so negative 500 e raised to the negative 0.5 t. Next, when you're trying to take the ln of something, the derivative of that is going to be 1 over the something times the derivative of whatever is in the denominator there. So here the derivative is going to be, so the derivative of ln of cos is going to be 1 over cosine of x multiplied by the derivative of cos. Well, the derivative of cos is negative sine, and that's attached by multiplication. You can rewrite that as negative sine x over cos x if you prefer. And then if you kind of write it like that, if you think of this as, or did I say that right? Is negative sine x over cos x. And if you remember from pre-calculus, you can then rewrite that as negative tan x. So if that was a multiple choice, just be careful. They may have reduced it, and that is still negative though, so just be careful there. And finally, we're moving right along to G. So in G, okay, be careful. I would rewrite the original here because this squared is on the tan, but it's not on that 5, okay? So this is the same thing as if it was 5 and then tan of 5x, that part, squared, okay? And I think when you write it like that, it makes it a little bit easier to see that you want to use the chain rule. So when I take the derivative, this is going to be h prime. So when you take the derivative of that, it's going to be 2 times 5. It's going to give you 10. You recopy what's inside, and you decrease the variable, but that'll just be a 1. So it's going to be 10. And then that's tan of 5x. Okay, but then remember, we need to take the derivative of that. Well, how do you take the derivative of tan to the 5th? Well, very similar to our notes from day 1, that's going to be another chain rule inside of there. So the derivative of tan is secant squared. So it's going to be secant squared of that thing. But now I have to take the derivative of that because I still have that parentheses. So the derivative of that is going to be a 5. Okay. You can then multiply this 5 with this 10 if you wanted to kind of clean it up just a little bit and rewrite it as 50. Tan 5x secant squared 5x. And I would leave my final answer like that. Okay. Last one for this number 1. I would rewrite the original again. Whenever I see a square root, I should be thinking raising that to the 1/2 power. This square root is in the denominator. So when I rewrite it with that in the numerator, it's going to become x squared plus 1 raised to the negative 1/2. Okay. And now I can use chain rule again. So again, now I'm taking the derivative, so I can use that that notation of y prime. Negative 1/2 times 1 is going to leave me with a negative. You can write a negative 1 if it makes you feel better. And I recopy what's in the parentheses. This time it's an x squared plus 1. I decrease the power by 1. So if my power was negative 1/2 and I subtract 1, that's going to be a negative 3/2. Okay. And then I need to multiply that by the derivative of what's inside these parentheses here. So the derivative of x squared is just a 2x. And you probably would bring that out front, so it would be negative 2x times this, negative 3/2. And again, if you wanted to rewrite it again with this in the denominator, so it would be negative 2x over the square root of x squared plus 1 power over root. So that would be to the 3rd power there. Okay. And that's all number 1. So now I'm just going to scooch this up so I could tackle number 2. All right. In number 2 here, it says, basically I'm just asked to find the first derivative. Then I'm asked to write the equation of the tangent line at 0, and then find the second derivative. So these are all talking about that first problem. So this is going to be a chain rule here. Okay, so when you're finding the derivative, we are just going to rewrite that times the derivative. So, okay, the derivative of sine is cos. So the derivative of this, you're going to say it's 4 cosine of what's in the parentheses there, right? Multiplied by the derivative of that. Well, the derivative of what's inside here is a 10x. So there's that. Again, if you wanted to rewrite that as 40x cosine 5x squared, that's fine. And now we're going to write the equation of the tangent line at x equals 0. So we have a derivative from part A, and now we're just going to evaluate that derivative at 0. So I'm just going to say dy dx evaluated at x equals 0. That's just showing that I'm plugging 0 into the derivative. So if I plug 0 into the derivative there, well, that's interesting. That's going to give me just a 0, right? Because if I plug in 0, that'll be 0. Cosine of 0 is 1, but 0 times 1, right, is going to be 0. So you can even write that if you wanted. Okay, so I have a 0. And I'm writing the equation of a tangent line. So this is the slope at that point, okay? But if it asks you to write the equation of a line, right, you should be thinking y minus y1 equals m, parentheses x minus x1. Not that it's going to matter much here because this is going to be 0 times whatever. You don't care. It's going to be a big old 0. And if I plug in 0 into the original, okay, sine of 0 is 0, so it's going to be more zeros. So it's going to be this minus 0, this minus 0 there. So basically you just get y equals 0. And you're done there. Don't let the zeros fool you. It's perfectly fine to have 0 as an answer. And let me just scooch this up a little more so you can see. Okay, and then the last one on this page, it's just asking you to take the derivative of something you already took a derivative of. Okay, so now I'm working with this part from A, and then you have to take the derivative of that. So when you're taking the derivative of that, what I would do is kind of think of this part here as part 1, and then this part as your part 2. So I'll just kind of label that part 1 and 2. And you're going to have to use your product rule here. Okay, so remember, product rule says first times the derivative of the second plus the second times the derivative of the first. So that's what we're going to use to come up with, let's see, so we're going to have first times the derivative of the second. Now the derivative of the second, within there is a chain rule, okay? So this is a little tricky. So if I asked just for the derivative of this, well, the derivative of cos is negative sine, so it's negative sine of that thing, okay, times the derivative of the inside there. So that's times 10x. Okay, so remember, we're still in this big product rule though. So we have first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of the first is a lot easier. So that's going to be a 40, and you've got that. Okay, and oh, that's all we had to do. So you can clean it up if you want, or you can leave it like that. And that is the front of your homework, okay? Okay, you can stay tuned for part 2. Okay, and I want to... Okay, this is part 2 of the chain rule homework from Unit 2. So in number 3 here, it says you are given an h of x, and that is a product of these two functions here. And it also gives me k, and it says that k is f of x cubed. So that's a function inside a function there. So that kind of leads me to believe I'm going to be using some product rules and some chain rules in there. So in the first one, it says that I'm trying to find the derivative evaluated at 1. So I think it would be helpful to actually, above it, maybe write how I would find the derivative of h. And I'm purposely writing that above because, especially for part B, you'll need a little bit more room than I gave you there, sorry. So I'm just first going to write what the derivative is. So the derivative of h with respect to x, okay, if I was just taking the derivative, this is a product, so it would be first times the derivative of the second plus the second times the derivative of the first. So I'm just going to write that. So that's first times the derivative of the second plus the second times the derivative of the first. Well, the derivative of the first is going to be the 2x there. Okay. So now we are just going to plug in 1 for the x values there. So to evaluate this, we'll say that that's going to be, well, if I plugged in a 1, 1 squared is just 1. That part's easy. And then the derivative at f of 1, well, according to this chart up here, the derivative at 1 is -2. So I'm just going to multiply that by a -2. And then plus f of 1, according to the chart, is 3. And multiplied by 2 times, if I plug in a 1 there, is 2. So for this, I'm going to get -2 plus 6. So my answer is going to be a +4 for my final answer there. Okay. Similarly, when you do this with the second derivative, it's actually going to get pretty yucky. It's going to be really, really long. So I'm actually going to, can I fit it up there? Let's see. I'll write it up here. So the second derivative with respect to x, I'm going to kind of write out the rule for it, and then we'll kind of plug in afterwards. So the second derivative, well, guess what? That means I'm taking the derivative of the derivative. So I'm going to have to do a product rule here, and then another product rule there. So here it's going to be first times the derivative of the second. Well, the derivative of f prime is f double prime, so it's first times the derivative of the second plus the second, which is just f prime, times the derivative of the first. Well, the derivative of that is 2x. So that takes care of the first chunk. Now I need to go ahead and work on this next chunk. So I'm going to have to use product rule there again. So from there we have first times the derivative of the second. So it's first times the derivative of the second, which is just 2, plus the second, which is 2x, times the derivative of the first, which is just going to be f prime of x. Okay, so now for this h double prime here, I'm going to plug in a 1 for all of those things. So when I plug that in, 1 squared is just 1. Then when I plug in a 1 here, that's f double prime of 1 is 2 according to this. Plus f prime of 1 is going to be a -2. And when I plug in a 1 there, I just get 2. So now I'm over in this section here. If I plug in a 1 there, f of 1 according to this is a 3. That's plus a 3. Close parentheses, or now start a new parenthesis. So that was a 3. And multiply that by a 2. Plus, when I plug in a 1 there, I just get a 2. And then when I plug in there, I get a -2. So hopefully I plugged all that in. That gives me 2 minus 4 plus 6 and a -4 again. Okay, so then you can add all those together. Oh, and that just gives me a 0. So I have a 0 there. Okay. Very similarly, you can kind of work out the other two. Okay, and I can provide you with those answers there. Hopefully I did them correctly. So for this first one, if you work it out, I got an answer of -6. And for this part D over here, when I worked it out, I got the answer of +6. Okay, so you could try those. This time when you're doing it, you're going to have to use the chain rule, okay, because you have a function within a function, but it's similar to the others, so you could practice those. Okay. All right. At what point on the graph of y equals square root of 2x minus 3 is there a vertical tangent line? So, vertical tangent lines. You should kind of be thinking to yourself that there is a vertical tangent line, okay? You should be thinking the denominator is 0, right? So slope of the tangent line, you're thinking slope. Slope in calculus means derivative. So really what this is saying is take a derivative and then you're probably going to end up with some sort of a denominator, because that's how you're going to get a vertical tangent line there. So we're going to take a derivative and then set the denominator of that derivative equal to 0. So that's our goal. So first what I'm going to do is recopy or kind of rewrite the original. Again, when I see a square root, I'm automatically thinking of that as to the 1/2 power. And now I can take the derivative of that, the derivative of that. Let's see, so that's going to be a chain rule, so that's 1/2. 2x minus 3, subtract 1 from the exponent, gives me -1/2, times the derivative of the inside, which is just a 2. And this 1/2 and that 2 are going to kill each other off. So I have the derivative of being 1 over the square root of 2x minus 3. Sorry, that got a little bit squished. Okay, and so we are going to set that. So the vertical tangent line, you should be thinking set denominator equal to 0. So this, okay, we're going to set that equal to 0. Square both sides, and then subtract 3. So you get this, and then I got x is going to be 3 over 2. So that's going to be the x value, and then we make sure we are answering the full question. It says a point. If I just give an x value, that is not a point. So make sure you go back and find the y value. And so you can find the y value by plugging in to the original. So 3 minus 3, right? Because if you do 2 times this, it just gives you 3. So 3 minus 3 is 0. The square root of 0 is 0. So the point would be 3 over 2, comma, 0. And we got that one done. All right, moving right along. So 5, find the equation of the tangent line to this graph at the point. Oh, so this is nice because they gave us the x value and the y value of the point. Okay, and the equation of the tangent line, when you see equation of the tangent line, you should be thinking take a derivative, then use the point slope formula. So I'm going to take the derivative and then use the point slope formula. So the derivative, all right, so the derivative of e to the whatever is, you recopy the entire thing, then you just take the derivative of the exponent. So if you kind of recopy the entire thing, okay, just how it is, and then you multiply that by the derivative of whatever the exponent is. So the derivative of that is 2. And of course, yes, you can clean that up into -4e raised to the 2x there. So we've got that as our derivative. Okay, so that's what our y prime is. Now we're going to evaluate that y prime at x equals 0, because that's what was given. So to denote that, you'd say y prime of 0. So if I plug in 0 for x, 0 times 2 is 0. So we are saying this is e to the 0. And hopefully you remember that anything raised to the 0 is 1. So there you just get a -4 for the slope. And we are answering the full question, so we need to write the equation. So again, you're going back to y minus y1. Well, it's y minus a negative turns to a plus, equals m. The m I solved for was over there, that -4. So -4 parentheses x minus x1 is 0. If it is a free response, you're going to leave it like there. It's your safe stop. If it is a multiple choice, they will probably have them foiled and written out like this. So there's your answer there. Okay. The next one, okay, remember that the secant line is an approximation to the derivative, and the secant line has 2 points. If there is 2 points, you can calculate the slope, just like you did back in the day. So let's see. So estimate the rate at which the child is growing. So estimate tells me I'm going to be able to use the squiggly instead of the equal sign. So I'm really trying to figure out the derivative at 11. So h, I'll call that h for height, right, at 11 is approximately, this is an approximation. So we're just going to use, if you realize 11 falls right here, so that means that this, the 10 and the 12, and those are going to be important. So basically it's h of 12 minus h of 10, all over 12 minus 10. minus 10 there. And you can go ahead and grab all that info from the table. Over 2. And I think that ends up to be 6.5 if you type that in correctly. Okay. So there you are. There's the approximation. Okay, and for those of you that kind of hung with me, I wanted to go back and kind of show you those answers after you had a chance to work them out. What I did for k prime and k double prime over here, I actually kind of worked out this is what the derivative is in the terms, and then this is me plugging it in. And for k double prime, I actually worked it out up here what it should be so that it wasn't so squished. And then I plugged it in for you down there. So feel free to pause the video at this time if you need to kind of pause to check your work. And then also at the very bottom, I also included the answer there. So, all right, have a great day, and I'll see you in class. Bye-bye.